Okay, good. So yeah, so I wanted to start by being curious how your final project's going. So even though I was horrible about being in here last week, this week I will be here, and I actually love to catch up with you in terms of your final projects and what's going well, what's going wrong. So feel free to catch me either during the office hours or even I will be around in my office. So if you are coming by, just swing by. In the worst case, I just won't be able to accommodate you immediately. But I would love to see how are you guys doing. So what I want to do this week, essentially, this lecture and the next one, is to sort of, it might look like going back to when we talked about implicit Euler. And I want to do the advanced stuff I was sort of mentioning before when we talked about implicit Euler. The thing is, we didn't really do it properly. And actually, fairly few people know how to do it properly, and I will explain what I mean by properly. And the interesting thing is that there is a connection between what we already talked about, time integration, implicit Euler, and optimization. So that's what I mean by the variational. This is not to be confused with different meanings of the word variational. Some people use variational integrators to mean symplectic integrators. This is not it. This variational means essentially optimization. So what I mean is, and what I will show you today, is that we can rewrite implicit Euler time stepping as an optimization problem. And that's very cool because it opens up this entire, I would say, industry of optimization techniques or mathematical programming. Have you heard of linear programming, quadratic programming, those things? So these are the first chapters of optimization. The thing that's really popular today is convex optimization. And that's where this will take us. Even though it will not be entirely convex, we can still use some of the tools of convex optimization. And there are some very powerful tools there, and we can combine it and get a really good solver for implicit Euler. And what we'll probably do the next lecture on Wednesday, I will show you how to get even better solvers than the standard Newton's method. Okay?
Quick question.
Yeah?
Is this something that would get applied to like plot simulations and stuff?
Plot simulations? Yes, yes, yes. So I'll be discussing it on the example of deformable solids. But as you know, this is more general than that, right? Like, I remember when the position-based dynamics came out, I was like thinking, could you do something like that for fluids? And then I sort of discarded the idea that I thought that the US Thomas method already was doing that, and so just to later find out, oh, not really, right? Like, and there was this new position-based fluids paper come out, right? So these things are general, but I will talk about the specific case of deformable solids. Also because this is relatively recent stuff. This has been explored. I mean, okay, it's been known for a while, but in graphics or at SIGGRAPH and so on, people started looking into this like only relatively recently. I think the paper I learned about this first is from 2011, the example-based elastic material. So this is not super well-known thing in graphics. It may be that like in physics, this is already well-known, but that's.
I think by 62, we went through like not variational, but something like a Backtracking paper about
Barofitkin. So we also talked about Barofitkin, right? That's a great point actually. So why Barofitkin is not already it, right? I'll explain properly. So Barofitkin is what's sometimes called semi-implicit method, in the sense that it only does one iteration of Newton. Okay, and after, maybe it will make more sense after I laid out the basics. But Barofitkin is not really solving the implicit Euler perfectly, and it can be unstable too. It's much more stable than explicit methods, but you don't have any guarantees there. What is in the paper actually, in the Barofitkin paper, and the simulator is still being used at Pixar, so it's still a very good simulator with some improvements. But what they do, if things are starting to go south, like something starts exploding maybe, so don't think that the Barofitkin would never explode, it can. And the trick, do you know what's the trick they do to avoid? They detect if things are going weird, like if something is going out of bounds, or actually I'm not sure how exactly do they detect it. That will be another interesting thing. But what do they do is they just lower the time step. There's damping. That's one. There you have this bag of tricks, right? There is damping, and then you can decrease the time step, right? Decreasing the time step that almost always helps at the cost of more compute, right? But okay, but let's go through this. It will actually all make more sense after we have made this connection. So I said we will be discussing about, oh wait, did I want to say? Oh, I had one more thought when I was preparing for the classes. I was thinking I would like to get your feedback as we can have this interactive opportunity. Because I was thinking that what we are doing for the second part of the course might be actually wrong. We are trying to teach something that might match our final projects, but we are almost never able to make everybody happy. So I was actually thinking that maybe the right way to do this course, that the second part would be like a seminar type of thing. So actually you or the teams would be presenting the topic you are working on, and we would actually have a discussion about it. Do you think that would work better than just doing the standard lectures like I'm doing right now? No?
I think discussion is good. I'm not sure like a formal presentation is it?
I'm actually presenting like you're usually implementing some paper, right? So since you have to understand it, you could as well present. You think maybe it's not such a great idea?
No, I mean we already do it at 660.
Yeah, I know it's done in 660. Yes, yes. Okay, let's think about that. It won't affect you anyway because I'm not changing this course. I was just thinking more for next year. All right, let's get down to business. So let's simulate some deformable solids. So I mean hyperelastic materials. So like my favorite elastic objects that cannot break. They can squish and stretch, but they will always return to the rest pose. Okay. So we need this is sort of like a recap. We need discretization in space and time. So let's assume this is my favorite elastic object to simulate. Let's see if I can get this. That's an elastic object. Let's just assume in 2D, 1D, doesn't matter. So the first thing we do spatial discretization, okay? So we discretize the space, and you, yeah?
Is there a way to lock the focus?
Oh, sorry. Yeah, thank you. Sometimes this happens. Better? That's better. You had the finite element method, right? And then explain you the finite element method. So now you know at least two ways how you can discretize the space, right? One is what we talked about first, the mass spring systems, when it means we just sprinkle mass particles somewhere somewhat intelligently on our object we are trying to simulate. And the finite element method would essentially mean creating a mesh and working in some finite dimensional function space. Either way works in this case. So I will be talking to make it easier for the case of mass spring systems here, or let's just assume we sample it with mass points here. But the ideas would generalize in a fairly straightforward way also. Yeah, these ideas would generalize in a straightforward way to finite element methods. Okay. The point of the space discretization is that we convert the continuum to something that has a finite number of degrees of freedom which we can compute on. Okay. And speaking of, so let's just not complicate things here because the finite element method is not my point here. So let's just say that we are doing the mass points. And we can just concatenate all of their coordinates in a vector. So if I have m mass points, so the number of points here would be m, then I have a 3m vector which describes the state. Okay, some state would be the rest pose, some q0 or whatever we want, doesn't really matter so much here. And the q would be the current pose. So somewhere you initialize it and you simulate, right? We know this. So the second discretization we need to apply is what? It's time, exactly. And there we do the standard thing, right? If this is our time axis, so here goes time. Start at some t0. That's where we are starting. So there is some initial condition there, maybe zero velocity, right? And maybe the snail is sitting somewhere. And some forces will start acting on it, and we discretize the time. And again, let's make things simple. So we will just say that there is a constant step size h. What is your favorite step size, time step? 0.0.
30, I guess. 1 by 30?
1 by 30, that's my favorite step, yeah, because that's that's roughly like, yeah, 1/30th of a second, right? Why is it my favorite step and yours too? Because that's equivalent to the frame rate of a video you want to ultimately render, right? If you are doing 30 frames per second video. So that's a nice one. If we can simulate things with this time step, then that will be good. And then we just split the time into these small chunks and we simulate. So let's, by convention, let's say that state at time Tn will be denoted as Qn, okay? And that's of course the 3m dimensional vector, as I said, at every time, okay? So that's this. So the next thing we will need are forces. So I'm essentially recapitulating things you you already should know. And let's do just position dependent forces to make things simpler. There are also damping forces which can be velocity dependent. Let's not complicate things yet. Let's just do the position dependent forces first. So what are forces if they are just dependent on the state? So the forces are a function which maps from the state to a vector of forces, okay? So it consumes the state and tells me what force acts on each particle, okay? And I sort of prefer to have this abstraction there because then it again encompasses both mass spring systems and the finite element method, right? Even if the finite element method ultimately will get some function which for a given state computes forces. So it's really general. But again, if you don't want to care about the finite, if you want to do just a mass spring system, that's totally fine. That's all you need to think about. Now we will assume that the forces are conservative. What does it mean that the force is conservative? That's this thing in physics, right? That means, what is it?
The work done is like same. The work done by the force is same if you move from point A to point B.
Exactly. The work does not depend on the trajectory. And the consequence of this is that you can write the force using a potential, right? So that means that there exists a potential function E, which is a function from 3m to r, such that the forces can be written as the negative gradient of the potential, right? So if you have a conservative force field, you can find a potential. Forces are the negative gradient of the potential. That's one of the ingredients we will need to get to the optimization formulation.
Sorry, I didn't quite understand. What,
the potential stuff?
Yeah. So what does it mean to be conservative? It doesn't depend on if you're going from A to B or B to A.
The work done by the forces does not depend on the path. So I guess I don't want to be explaining physics here. I'm not competent enough to do that. But I think ideally, if you have a force field there and there's a particle traveling from some state A to state B, it does some work as it goes. Like the easiest thing is like imagine some heavy object in a gravity field, right? I think that's how like the work was like originally invented in the 19th century or something. You were lifting water from a mine or something. So you're doing work in a force field, right? The gravity field is a perfect example. And the work done doesn't matter like how much you slide it sideways. All that matters is the way up. And the consequence of a conservative force field is that you can find a potential, like elastic gravity potential is an easy one, right? MGH, and the force is just the negative gradient of the potential. So that's what we'll need there. Am I saying it right? Okay. Okay, to make it, to just, I guess, refresh your memory, what specifically, we talked about these potentials for the case of mass spring systems, right? So if we had a mass spring system, and if I said that my state was consistent of particles Q1, Q2, up to Qm, each of them was a 3D vector, right? You know what? Yeah, let me call these P1, P2, and to PM. So it's not being confused by the time-dependent states, okay? So the undeveloped particles are P. So if I have the snail, maybe this would be P1, this would be P2, this would be P3. Does it work on this? P4, and so on, okay? Up to somewhere the tail would be PM. And then you would put some springs there. Somewhere. You can be creative about the springs, as you know, right? They can even go outside, doesn't matter. It's supposed to be like this. And then the potential for the mass spring system would be quite easy, right? What would be the potential for the mass spring system? Remember, there would be just sum of Hooke's laws for each spring, right? So for example, if I have a spring between P1 and P2, I would have some stiffness, K12, times the current length of the spring, P1 minus P2, minus the rest length of that particular spring, right? Plus for the same thing for another spring, for example, P2, P3. So this would be the stiffness of that 2-3 spring here. I'm going fast because we already had this before. So this should be just refreshing, and so on for all the remaining springs. Okay, that's the simplest potential you can work with, but it's already quite interesting potential. It does reasonable things, right? So that's clear? Good. So the next thing we need is a mass matrix. Mass matrix, and that's a matrix M of what dimensions? Just to check if you are paying attention. It will be also 3m by 3m. I guess that's sort of m by m. That would be also fine, right? Like the thing is that just for convenience, I just make the mass matrix with like the repeated entries. So the M1 would be the mass of the first particle. That would be mass of the second particle, and so on up to the last particle. Okay. Did I tell you before that there is this cute algebraic thing called Kronecker Product that lets you write it like this? Kronecker Product I3. I might have told you because this is my favorite type of product. That this product just says that replace each of the entries in the matrix by an identity, in this case 3 by 3 identity. So this is a 3 by 3 identity scaled by the scalar. Okay, and that just creates this. This is just a convenience, but once we'll be doing some algebra with it, which we might be doing on Wednesday, still to see what exactly we'll be doing, but that's where it will be convenient. Okay, so this is a mass matrix for the mass spring system. So it's just a diagonal matrix. The masses are of course positive, so this matrix is trivially symmetric and positive definite. The cool thing is that again, in finite element method, you also get a mass matrix. Did you study this? Did you discuss it with Tintin, the finite element method mass matrix? It's essentially a similar idea, except that the mass matrix does not necessarily have to be diagonal. They can have some off-diagonal terms, but it still has to be symmetric and positive definite. Shall I mention that briefly? What is the difference from the finite? Basically, the difference, it's sort of like subtle. So let's not dwell on that topic too much. I guess the point is that in a mass spring system, you have all the mass concentrated at these points, right? If you think about it. That's certainly wrong, right? The mass should probably be like distributed uniformly, right? So the finite element method mass matrix essentially, instead of concentrating the mass at a point, says that the point essentially moves a function, and the function has some masses associated with it everywhere. And after you do the math, it essentially boils down to a mass matrix that has off-diagonal elements which correspond to the neighbors of the particle. So if this was a finite element mesh, then this guy would have some masses also with these particles. Not a big deal, just a slight difference. And by the way, even in finite element methods, what people like to do is what's called mass lumping. That means that they essentially scratch it and replace it with the diagonal mass matrix anyway. Okay, so that's just so you're not surprised if you see some more exotic mass matrices. Okay, so let's get back to physics. So one more notational thing. So the velocity at step n, I will denote as Vn, and by definition, that's just the time derivative of the state. Okay, that's my velocity. So now I can write the implicit Euler update rules. So what I'm trying to do is to formulate implicit Euler as an optimization problem, to build this connection to optimization, or the optimization is also called mathematical programming for some historical reasons, or mathematical optimization, mathematical programming. It means the same thing. So what are the update rules for implicit Euler? So there are two. So the first one is how do we update state? Well, we update the state. So this is, so if, you know what, let me first write it, then I will talk about it. And the rule number 2 is update for the velocities. Maybe I should write it like this, right? Like assignment or whatever. Plus HM inverse F Qn plus 1. So here, if you are paying attention, here the 3m by 3m mass matrix is immediately useful already because I can just multiply the forces with it and everything works right out of the box. So the first update rule is the update rule for the next state. So I assume I already know the state at time tn, and now I'm going on to computing the state at tn plus 1. And I need to compute the positions and the velocities, okay? And implicit Euler has this weird quirk that instead of using the quantities I already know, such as Qn and Vn, it's using the quantities I don't know yet, right? That's a weird thing about implicit Euler. That's what makes it powerful, but also complicated, right? So essentially, this one will be how to deal with that complication in an elegant way, as opposed to sort of sweeping it under rug and then hoping that things will work. That's the alternative. So let me just point it out here that Qn and Vn, we know this, that's known. And Qn plus 1, Vn plus 1 are not known, unknown. That's what we need to compute, okay? And the Borov-Witkin way would be now to do a Taylor expansion of F and get a system of nonlinear equations which we approximately solve using one step of Newton's method, okay? But here is the cool thing we can do instead. Instead, we can rewrite this as an optimization problem. So let's see how this is done. This is sort of cool. So first, I multiplied this by. No, I don't multiply it. I just isolate the velocity. So if I do Qn plus 1 minus Qn, that will be h Vn plus 1, right? And if I write the same formula for the previous step, I will get that Qn minus Qn minus 1 equals HVN, right? That's the same update rule for the previous step, okay? Because it applies, of course, at every step. And now what I can do is I can multiply this by h. So let's do that. So I'll get HVN plus 1 minus HVN. Is that what I wanted? Let's see. I think so. And that's equals h squared m inverse f Qn plus 1. Okay, so what I'm doing here is I'm massaging the update rules to transform it into a little bit different form. Okay, is it all clear? If not, interrupt me. Now what I'm gonna do, I will take this. So this HVN plus 1 I can substitute by this. And this HVN I can substitute by this. Okay, so if I plug it in there, I will get here Qn plus 1 minus Qn. And this is with minus, so here's another minus Qn plus Qn minus 1. And that equals h squared m inverse f Qn plus 1. That's not changed, okay? So what we have here on the left-hand side is Qn plus 1 minus 2Qn plus Qn minus 1 equals h squared m inverse f Qn plus 1, okay? Everybody got it? It's a very fairly simple math, but somewhat nice result, right? This form. Does this look somewhat familiar? Let me make it even better. I can divide by the 1 over h squared, right? So in that case, we get on the left-hand side, we would get this. That should definitely ring a bell, if it hasn't already. What is this? Yes, that's a finite difference approximation of a second derivative, aka acceleration, right? So this is essentially an approximation of what I could call like an acceleration at step n, okay? So this is essentially, like you can immediately recognize there the Newton's second law of motion, right? Acceleration times mass. I could also multiply with the mass matrix, put it on the other side. So m times a equals f. That's all that physics-based animation is always about, right? Okay. Okay, so what are we gonna do? So let's stick with this form. Because what I'm gonna do first, I'm gonna change the notation a little bit. So first, let's realize that these guys we already know. The Qn and Qn minus 1, that's already known, right? Those are the previous, that's what we already computed, okay? So let me say that I will call this y, just to simplify notation, okay? And the Qn plus 1, that's the unknown, so I will call that x. Yeah, thankfully I haven't used x before, so that's cool. So that's just really renotating this expression, so I get an easier formula to work with. So after I do this is really just a substitution, right? Nothing special there. And the point is that the y is known, and the x is what we need to solve for. Okay. So again, now you could again do the same Barov-Witkin thing, right? We just made like few trivial modifications. We haven't changed anything significant. But let's see. But what we can do now is now we can convert this. Now it's ready to be converted to an optimization problem. Okay. So what this is a system of nonlinear equations. That's because the force is nonlinear, right? And it's a system because on the right-hand side, on both sides are 3 m-dimensional vectors. Okay. And what I can say is that the solutions of this system of nonlinear equations are equivalent to critical points of a certain optimization problem. So I'll write down what that optimization problem, the critical points of certain function, okay? So that function will be called gx, and I will define it like this. Then I will explain you. Maybe you will see it yourselves. Where did that come from? Plus h squared ex, okay? And now what I claim is that the critical points of this function, what is a critical? Critical point is where the gradient is 0, okay, are exactly the solutions of the implicit Euler system, okay, of this, okay. So let me write it properly. The gradient of g is 0 if and only if this formula is satisfied. X minus y equals h squared m inverse f of x. Okay, so these are the forces. This is the energy potential. Okay. Why is this true? Because if we take the gradient of g, what do we get? Our favorite differentiation exercise, right? So this would be mx minus y. That's the first term differentiates to this. And what do we get by differentiating the second term? The derivative of the potential minus f of x, right? Minus h squared, exactly, f of x, right? So if I set this to 0, if I say the gradient must be 0, then what do I get? Well, let's try it. X minus y minus h squared f of x equals 0. Well, that gives me, I need to put the mass matrix on the other side, but that's easy, right? F of x. And then I can just multiply by the inverse mass matrix, but because it's positive definite, unless you're playing some sort of zero mass games, then you would get in trouble. But if all your masses are non-zero, strictly positive, then you have no problem inverting the mass matrix, and that's exactly equivalent to this form. Okay. So indeed, the implicit Euler time step, the system of nonlinear equations that correspond to implicit Euler time step, can be written as looking for a critical point of this function. And we can interpret this function, actually sort of interesting to interpret this function. Because the elastic, so let's try to understand this intuitively, right? You can be looking at it, yeah, is there something wrong?
No. So we're dealing with, sometimes we're dealing with infinite masses,
Mm-hmm.
and we would start in inverse masses instead. That is, inverse masses were equal to 0.
That would be a problem. Then you could not invert the mass matrix, right? Well, actually, wait a second. That would be... Actually, that would probably work in this formulation and not work in this one, right?
I mean, how can we deal with infinite masses in that relation, where we're dealing with masses themselves rather than with inverted?
Yeah, that's true. No, yeah, you're right. You're right. You cannot build infinite masses in there. Yeah. You would have to. You would have to. You could do it. You could do it differently in this formulation. You could do it using Lagrange multipliers, for example. But let's not complicate things. Let's just assume now that the masses are not infinity and non-zero. That the masses are actually well behaved, or whatever you want to call it. Yeah, good, fine, thanks. Okay, so let's try to interpret this like intuitively. What does this? So this is something that's that should make some physical sense, right? So let's try to pick up the physical meaning of this. So there are two terms, right? This one term here and this another term here. This h squared is just like a multiplication by the time step. It's just a constant scalar, so that does not matter a whole lot. And the first, the elastic potential, that has a pretty intuitive interpretation, right? If it's a gravity potential, that means the higher you go, the higher the potential will be. If it's an elastic potential of a spring, means the longer the spring you stretch, the higher the potential will be, right? So this sort of measures how much energy is stored in the system, if you will. That's like one intuition. You can have pretty good intuition, I think. What about the first term? What do you think is the first term? It's also very, very cool. So this would be that's of course the elastic potential times the h squared scaling. That's a very good guess. Yeah, it's something very closely related to that. Maybe you could even call it kinetic energy. Well, let's think about it. What it is? What is the y at the first place, right? I just said that for convenience, we will say this is the y, right? But what does that y mean? So the y means, and I think I even did it. So the y is actually with the minus. It should be 2qn minus qn minus 1, right? Because I'm subtracting the minus here. So if I put the minus there, that will be right. So I can also write this as qn plus qn minus 1. Okay. And can you tell me what this is? The qn minus 1, that's if this is my time line, and this is qn minus 1, this is qn, and this would be qn plus 1, right? So then qn minus 1, that's nothing but, I think we had it somewhere, right? Oh, it's right here, right? hvn, right? Time step times the velocity at step n. Okay, so what is y? The next state, but not exactly. If that was the next state, you don't have to bother about the elasticity, right?
The explicit Euler method. Next step would have an explicit Euler method.
Next step of the explicit Euler method?
Yeah.
Not exactly. Or yes, but if you ignore the forces. That's the, yeah, it is, you're almost right. Or you were right. It is the next step if you ignore the elastic potential completely, right? So this is actually exactly Newton's first law. What Newton's first law says is that if there are no forces acting on the system, the potential is 0, or yeah, then what the system does, it just keeps moving with a constant velocity, right? Whatever velocity it had, like the space shuttle far away in deep space just keeps going, right? That's what it does. And that's exactly what this term says, or what the y is purely inertial motion. No forces are completely ignored, or the only thing that's not ignored is the velocity it had. So this basically says, the first term says the object wants to keep moving with the velocity it had. Right? If something was going very fast, it probably wants to keep going, right? So I like to interpret this as inertial potential. Because why potential? Because once I put it like this, I guess even easier would be think about something like this, right? XTMX. What is that? That's a n-dimensional quadratic function. It's a convex quadratic function because I said that the mass matrix is positive definite. So this is like this, if you visualize it like this bowl-shaped function, maybe in lots of dimensions, but it's just a simple convex quadratic function, right? And this essentially attracts the x towards y, right? Because what it turns out to compute the critical points, what we want to be doing is minimizing the g, okay? And minimizing the g essentially means minimizing the sum of, exactly means minimizing the sum of these two terms, right? And this is the beautiful intuition I would like to convey here, is that minimizing this essentially means looking for x that makes the sum of these two terms as low as possible, okay? So the one term says, well, you should be following the motion that the object had. You should not deviate from the previous velocity too much, because due to inertia, the object wants to go the direction where it was going before, right? But the second term says, wait a second, there is also some elasticity, right? So if the inertia means I will be stretching a lot, or I will be going up against gravity, then this term won't be happy. This is like the term say, wait a second, how about the potential, right? And if they both come to agreement, then you get the solution, which I think is quite beautiful interpretation.
What is the gradient of inertial potential then? Inertial forces?
I guess so. I don't know if anything like this exists, but I guess that would be inertial force, yeah. I'm not sure if that's the right physics though. I mean, this is just my terminology, yeah, so take this with a, maybe I should put it in quote unquote. This is just like intuition. This is no real physics or something. And by the way, don't forget that we are just talking about implicit Euler. Okay, that's what we are doing here. But that's a very beautiful interpretation of what actually implicit Euler is trying to do, right? And also tells you why this is more reasonable than explicit Euler. Okay, so now what we have done so far is converted the implicit Euler time stepping to an optimization problem. Now we know that all we need to do is minimize gx subject to x, right? We have some function, we need to minimize it. If we can minimize it, problem solved. Okay? And then if you want to play some games like some particles cannot move, then you could invoke constrained minimization, right? The beauty of this is that now we can switch to mathematical programming, essentially, because these optimization problems have been studied a lot, especially in the convex case. And even though this is not convex, it turns out that lots of the machinery of convex optimization still applies. So that's what I would like to do next, give you a brief tutorial on unconstrained optimization. Which is something that's a very useful thing, and not just in physics-based simulation, but in general, unconstrained optimization. Because that's essentially, if we take it from here, the problem is if you have some function g, where in our case g is a multivariate function, like 3m, for example, to r, let's assume that it's convex, because the convex optimization is the best studied part. So let's first discuss the convex case, and then I will tell you what do we need to do to deal with the non-convexities. Okay, there are some complications with that, but we can deal with that somehow. But the convex case is important. And I guess the one importance is that because it's a well-studied thing. Have you had some class on convex optimization, Newton's method? I know there is one, but it's an advanced graduate class. There is a beautiful, if you wanted to study, so this is absolutely general problem, by the way. You have a function g, maybe I should say what assumptions on g we have, right? So g is twice continuously differentiable. That's so our techniques work essentially, and we can also assume that it's bounded from below. Why do we assume that? Well, because if the function could go to minus infinity, that would be sort of sad to minimize it, right? Because we could go to minus infinity. So let's just assume it's bounded from below. Actually, some of the techniques even simplify things by assuming strong convexity. I guess I can. Well, I guess I can say it now. So strong convexity means, well, I guess. So what is one way how to tell if the function is convex? We talked a lot about Hessians if you still remember from the first part of the course. So the Hessian written like this, G, if the function is convex if and only if the Hessian is positive semi-definite everywhere. Okay? Positive semi-definite. And strong convexity means semi-definite, positive definite. The strong convexity means that there needs to exist some constant C such that even if I subtract C times identity, I will still get a positive definite matrix everywhere. So this is just a complicated way of saying that we don't allow locally flat regions. If it's a strong convex, if you imagine the bowl type of shape, it could be, because it has lots of dimensions, that in some of the dimensions it's actually perfectly flat. In that case, it can still be convex, but won't be strongly convex. Strong convexity means that there is always some non-zero curvature. That's essentially, it's sort of like a detail. Doesn't really matter this too much. Why I'm saying this, because this is a completely general problem which comes up in a lot of cases. I will be talking about applications in physics-based simulation, because now we discovered the connection between time integration and optimization. But optimization, of course, is much more general technique. It's used like in a lot of places in engineering, right? Electrical engineering, optimizing electrical circuits. It's used in image processing, medical imaging, a lot of areas. Okay, so let me tell you the basic techniques for unconstrained optimization. Did you have this in some class? I wonder. Okay, you did. You do? Descent methods and so on.
Gradient descent.
Hmm?
Yeah.
There's gradient descent, then there is Newton's method. Yeah.
Yeah, some little bit.
562, huh?
Gradient descent method was, but only theoretical.
Hmm?
Introduced this only.
Okay, so I will also quickly introduce it, and then I will tell you how to make it work for the case of physics. Okay. So basically, all these techniques are iterative, right? So they work that you start from some initial guess, x0, that will be my initial guess. And then we create a sequence, x1, x2, and so on, which converges to the solution, which is the x star. That's what we want to get. That's the solution. That's where the function is minimized. Again, unless it's strictly convex, the solution does not have to be unique. There can be multiple solutions, and so on. Let's not worry about that. In the convex case, the necessary and sufficient condition for the solution is that the gradient vanishes at the solution. So my gradient of the function g I'm trying to minimize at the solution must be exactly 0. Okay. In the convex case, by the way, that's the beauty. That's why we like to assume convexity, right? Because in the convex case, the problem of local minima and saddle points essentially goes away, right? In the convex case, once the gradient is 0, you know you have a solution, a global optimum, okay? In the strongly convex case, there will be just one. In the non-strongly convex case, there could be an entire subspace of solutions. Okay. Oh, by the way, speaking of initial guess, going back to our physics exam, that's what we care about here. What do you think would be a good initial guess? Almost all of these iterative techniques, gradient. I will talk about gradient descent and Newton's method for optimization, which is slightly different flavor than Newton's method for solving a system of nonlinear equations. Sort of the same technique, but it's different formulations. So, what do you think is a good guess for this particular optimization problem? I'll be minimizing this. So you are time stepping, right? Then you are solving the next problem. It seems that a reasonable thing would be to turn to the previous state for an initial guess, right? So one possibility in our case for the initial guess would be to just say that the x0 equals our qn, where qn is the state in the previous time step. It turns out there is actually a better option. There's a better initial guess you can make, which is almost always better. Exactly. The initial guess can be anything. So you can sort of say that why not step forward already? Qn plus hvn, right? Which is exactly what I call this y, right? This initial guess essentially moves it as if there were no forces acting on it, right? So the inertial motion is already accounted for in the initial guess. Oh, and by the way, this is, you might be surprised, this is essentially what position-based dynamics does, believe it or not. I will explain it the next lecture, because I won't have the time to do it today. But this variational formulation, this optimization-based formulation, optimization variation, the same thing, okay? That's essentially also why position-based dynamics works, or how you can explain position-based dynamics. So this point of view is very useful because it explains a lot of things. And this trick is essentially what makes position-based dynamics work. But I will explain that more next time, okay? So right now this is just an initial guess. In theory, for convex optimization, for any initial guess, you would get a solution. But good initial guess will allow you to get to the solution faster, doing fewer iterations, right? The name of the game is that to converge to the solution in not too many iterations, right? Because each iteration costs you some work, some computations. You want to cut that down. So the standard thing to do are so-called descent methods. Because we are living in pretty high dimensional space, right? Even for fairly coarse mesh, you can easily have thousands of degrees of freedom, right? So to deal with this too many dimensions, we are gonna descend only in one direction at a time. Okay, so the idea of descent methods is to pick a descent direction that is gonna be a 3m dimensional vector, and then minimize the function by going in this direction as far as we need to minimize the function, then pick a different direction. So let me write it properly. So we start, let's say, step 0 of the algorithm would be that x0 is our initial guess. Then there would be, I guess there would be like a loop, right? So I can do like repeat, and step 1 would be determine descent direction. Let's call it like delta x. That's how Steve Boyd likes to. Did I tell you about Steve Boyd? I guess I didn't. I think I forgot. If you want to find more information on convex optimization, there is a great book and online courses from Steve Boyd, a professor at Stanford, which is absolutely excellent. That's where I learned most of my optimization. And the book is freely available online too, and the courses too. Convex optimization. I just have to show you because it's a really good resource. Yeah, these guys. There's a book. There is an online course. They have I think even some course you can take. So if you want more details on this, there is like 600 pages worth of details, and they are really good. We actually read it almost completely by now, and it's all useful. But the basics I will basically cover today, the very basics. So first we get the descent direction, then we determine a step size. Step size t greater than 0. And number 3, we update. So we compute the next iterate, I plus 1. And it's gonna be the previous one plus t times delta x. Okay? And we are repeating it until oops, 1L, stopping criterion is met, is satisfied. So what would be, what is the typical stopping criterion? Is that the gradient of G is below some threshold epsilon. I guess you can probably be more, we probably don't have to be super sophisticated about this. I guess the only thing would be like what units the gradient is in, right? So that the epsilon is reasonable. But okay, so what's the main idea of the descent method? So we are in a high-dimensional space. I mean, you can be thinking about just two-dimensional space, right? Imagine this ball in 2 dimensions. You are somewhere, you want to get to the minimum. Okay? So this, like you can think about it like you shoot in one direction, you commit to a direction, that's the delta x, and then the step size, that means figure out how far in that direction do you want to go. Okay, so if picking the descent direction essentially means reducing it to one-dimensional minimization problem. Okay, we have some 3m dimensional, 2-dimensional, whatever dimensional problem. Once we pick the descent direction, we say that we are going to be updating only by t delta x. So the direction, the magnitude of this doesn't even matter, right? So much. Because we can be multiplying by whatever t, and we multiply by t such that hopefully the next iterate, if I compute the objective, the gxi plus 1 will be less than what we started with, gxi, right? So you want to progressively reduce it, makes sense, until we can't reduce it anymore, until we are at the solution. Yeah?
So I understand this. This might be naive, but I'm wondering how is this very different from what, let's say, a Jacobi iteration does in a linear system? So, like, don't you also converge in a very similar way?
That's a great question. So this thing you can apply to linear systems too. this directly applies. There is such a thing as, I mean, I didn't talk yet about how to pick the descent directions, but most of the technique are, some of the, maybe most of the techniques for solving linear systems can be formulated also in this way. The thing is that for linear systems, the objective would be quadratic. If it's symmetric positive definite system, it would be convex, quadratic, so the convex optimization would directly work. And you can indeed have, for example, gradient descent direction for linear system. It's not super efficient though. More efficient, I'm gonna get to that. I'm sort of getting ahead of myself because I'm trying to satisfy your quench your curiosity.
I mean, it's fine.
Okay, maybe it's better to get back to that. So what I need to explain to make this algorithm concrete, you can think about these are like abstract methods, and to make it concrete, I need to provide some implementation. So how do we pick the descent direction, and how do we choose the step size? Okay. So it's easier to do the step size, so let's do that first. So let's say that somebody will tell you good descent direction, tell you this is the right direction to go, okay? Well, then you are in a good shape, right? Because the remaining problem is just a 1D optimization problem, right? So determining the step size becomes just a 1D optimization problem. So essentially you have a situation like this, and if it's convex, it's like really nice because you get some bowl-shaped function like this, right? Here is where you are now, here is where you started. This is your direction in which you want to go. And you need to pick the t such that you lower this as much as possible, right? So there is such a, so ideal, this is, the exact solution of now this is called line search. Let's call it, let's just introduce this term. This is called line search because it means we are searching along the line determined by direction delta x. This is the line, and we want to find that such a t such that this function is as small as possible. So there is a thing called exact line search, which would give us to the exact minimum of that thing. usually you don't know how to implement this unless the function is very simple. But it doesn't matter so much because it turns out that it's not necessary to do the exact line search as long as you do a good enough line search. So all you need to do, the name of the game is optimization, right? So you just want to be minimizing the G. So you just need to reduce the G sufficiently, right? If you didn't reduce it enough, it will get resolved by next iteration where you'll pick another descent direction, again optimize and iterate, okay? So how, do you know, since some of you had this, do you know how the line search typically works? What you need to, so now here are looking for a one parameter t. If the t is just a scalar, it's also positive, okay? Because if t was 0, it means we are not going anywhere. T is negative, well, why don't you want to go t negative? We, I think I forgot to mention this. We assume, what means a descent direction? Descent direction means that if we go in this direction, the function g will be decreasing, okay? Mathematically, we can say that the gradient of g dot product with the descent direction is negative, okay? This just says that going in the descent direction, the function will be decreasing, okay? So that's why here it's decreasing. You don't want to go to negative t, because that would mean the function would have to be increasing this way, right? You don't want to do that. You want to minimize the function. Okay, so the standard line search, simple but quite effective line search is called backtracking line search. And the idea essentially is to start with t equals 1. So here we assume that the direction has some intelligent magnitude in it, that taking a step of 1 is as large step as you would want to take, okay? In Newton's method, actually, that would be a very good reason for that. But let's just assume that t equals 1 is the maximum step you want to take. But the problem is that if you took too large, if the 1 was too far, if the 1 was here, then you would be overshooting, right? It could be even, you could even, like this function would keep going up, right? So you could actually even increase it, right? You certainly don't want to do that, right? So the backtracking line search works like this. So start with this, start with t equals 1. And if it happened that if the function is too big, if x plus, you just look at the objective, you evaluate it at x plus t delta x. And if it's smaller than gx plus something, I will explain it in a second what this something means, the gradient of g transpose delta x, then we are done, then stop. So this means we are checking if the function has decreased enough. This is a measure of enough, okay? If it had not decreased enough, what are we gonna do? We're gonna say that we're gonna reduce t, beta t, where this alpha here and beta, those are some parameters of the algorithm. Alpha is a parameter between 0 to 1/2, and beta is between 0 to 1, okay? What the beta means is how aggressively are we lowering the t. So the idea of this is that if we make the t small enough, we will ultimately get close to here. And because the function is locally decreasing in this direction, we have to get some decrease at some point. We just have to, right, from convexity. Or not even from convexity, just from the fact that this is a descent direction. And the fact that this already was not a minimum, because if it was, then we would stop. So the typical values that beta that people use could be like 0.1, that would correspond to pretty crude search, right? Because that means you try 1, you try 0.1, you try 0.01, 0.001. Very quickly you get to very small numbers, right? And there's somewhere you better reduce your objective. So if you want to do less crude, you could do like 0.8, less crude. What means this thing? This means, so if alpha was 1, this would be the slope of the tangent line at this point, okay? So this is sort of like the most optimistic estimate. The most pessimistic one would be that you would just want to get, so if this is my gx, you just want to get below your original gx. Okay. You would just say that you just want to improve it at least a little bit. If a was 0. If a was 0, then this term goes away, right? And you just are asking for t such that gx plus delta tx is less than gx. It's less than where you started. Now it turns out that this would be asking for too little, that you could make a very little progress, like tiny, tiny progress. And since you are doing some computation, you want to get something back, right? So you can be asking for something more aggressive, and this alpha essentially means interpolate between this one extreme case and this one extreme case, okay? So like a good choice of alpha would be something like this. It would be like, say, alpha equals 0.3, something between, typically something between, let's say 0.3. Typically you want to use something between 0.1 to 0.3. And that means that the line search will stop as soon as you get below this line. Okay? You would never be able to get below this line. You would be able to get too easily below this line, so you sort of like slant it down a little bit to make some progress, and the line search will stop as soon as we'll get below that. This is sort of to guarantee that you are getting some progress in each iteration. That's, I guess, the only tricky part of the backtracking line search. But okay, does that make sense? And that's all in terms of line search.
I'm kind of wondering about, so this line search problem gives us a good, so I'm kind of wondering about the initial guess, right? So the initial guess, I feel as if you took the wrong guess, you can get stuck at a minimum which is not the true minimum in that range.
Yeah, so that's why we have the convexity assumption, so that this cannot happen, right? Yeah, right. In the non-convex case, you could be in a situation like this, right? or that there would be like another false local minimum, which is not the global one, right?
This one,
yeah. So that's that's how the convex optimization people get around it. They just say this is not possible, right? Because this function would not be convex. In physics, we will have to deal with it, and I will tell you once we are done with this how to deal with that. So this is line search. This is fairly simple thing. It's just 10 lines of code, even with like lots of printouts and stuff. The harder thing is determining good descent direction. Okay. So as I said, the algorithm looks like this. First determine descent direction, then line search to determine the step size. So line search we already know how to do. The backtracking line search works really well. It's really simple to do. No big deal. The descent direction is a little bit trickier. You might be thinking, why is that tricky? Determining descent direction delta x. So what's the first thing you would think about? And you probably heard it before, right?
The gradient.
Gradient descent, exactly. So the first idea is gradient descent. And that's absolutely natural thing to do, right? You just say that the descent direction, by definition, is the negative gradient of the function. Of course, because that's the direction where the function will be decreasing the steepest, right? You're somewhere, you look like if you are a ball, that's what you do, right? And rolling down the hill in a gravitational field, that's the direction you will roll down, right? That's the idea of gradient descent. So in our case, we could directly implement this, by the way, which is sort of interesting. This only gives you one method to solve implicit Euler, which is not entirely obvious, right? You could just apply gradient descent to this. We did that with Tintin, I think 2 years ago, and we found that it converges absolutely horrible. You could just compute the gradient, right? No big deal. There is force, there is your inertia force, we can call it inertia force. And just apply gradient descent to it with backtracking line search. It solves the problem modulo the non-convexity. In the convex case, it solves the problem, right? Because this is always a valid descent direction. So this is an absolutely correct algorithm. The problem is it converges very slowly in practice. Do you know why? Here is an. That's the slightly tricky thing, and that's essentially the reason why we need Newton. So I borrowed this slide from Boyd, because here is a very clear example why the gradients descend, which sounds like a great method initially, why it's not such a great idea when you actually try to run it, because it takes a lot of iterations. So let's try this dead simple example, which is just a convex quadratic function in 2 dimensions. Okay, it doesn't get easier than that. But here this is the typical bowl shape type of thing. Here the tricky thing is that we put this gamma here, which is a scaling on the second variable. So this gamma, if these are the isolines, if you look at it as a bowl from above or something, then the gamma tells you the scaling on the y-axis. Okay, if gamma was 1, this would be circles, and the small or the larger the gamma here, the more squished this thing is. Okay. It turns out for this simple example, we can actually do exact line search, because for any direction you will just get a quadratic function. We know how to minimize quadratic function. We can compute the exact step size, so the line search does not get better than the exact line search. So if you were to blind line search, you would be wrong, because here you can, because here we are doing the perfect line search, the best line search in the world. And here are the iterates you will get. So we can plot it. And if you plot it already for gamma 10, then you find out it does this. It does, and then it gets to the optimum, right? The optimum, of course, is at 0, right? It's a non-negative function. You can get it to 0 at 0. It doesn't get below 0, so the optimum is, of course, here. But the gradient descent takes a lot of iterations to get there, okay? And it would get worse if I made the gamma even larger. Right? I think you can even compute, I don't think it was done here, you can compute how many iterations does it do in a relation to the gamma, and the higher the gamma gets, or the lower actually, if you go to very small, then that means you are squishing in the other direction, right? Then it's also bouncing off a lot. Can you like see the reason why that is? It sort of makes sense, right? Like imagine this parabolic bowl which you squished, right? And then drop. You don't drop it from the center. If you were lucky enough to drop it from the center, I would actually go down immediately, right? But you put it a little bit off center, and what the ball does is like clink, 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 clink. Because the point is that the gradient descent is not pointing you to the solution. It's pointing you in the. It's like really greedy algorithm. That's another way you can understand this, right? It goes greedily in the direction where locally you're optimizing it the best, but that's not the best thing to do globally, right? It's like the greedy algorithm for chess or some other game would be just like take the biggest piece, right? That would not work very well. So that's the same thing here. So the way to improve the convergence. This graph?
Yeah.
Oh, sure. Yeah, sorry, I thought it was obvious. You start here. This is x0. This was my initial guess, okay? Notice that it's a little bit off center, right? The center is here. Okay. So here, I guess would be, I don't know if you could visualize, you can like visualize it. This is a function that goes up, right? It's a parabolic ball which is squished in this direction. These are the isolines, right? If I'm cutting, slicing with planes, I will get these ellipses.
It's this way.
Hmm?
It's like a squished ball.
It's a bowl. Now I wish I printed a 3D thing, but we had this before, right? It's a quadratic function in 2 dimensions, right? If the gamma was 1, it would be perfectly quadratic. It would be with shapes like this, like this. Yes. If the gamma was 1, it would actually be in a spherical or circular bowl. The higher or lower the gamma is, the more elliptical the bowl gets. Okay? You start at x0, and you evaluate the gradient. That's the steepest descent direction. And the steepest descent direction points you here. in this direction, okay? Imagine you are a little ping pong ball or something in this parabolic ball, and you just roll down. It would be actually nice to sort of manufacture it, because then it would be super clear. You would see the ball going. So you compute, this is the gradient direction, and you compute the optimal step. The optimal step gets you here. Then you compute the gradient direction, that gets you here, 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 and so on.
That's the second part that I don't understand.
Which second part?
The second part, that why would the gradient point in an opposite direction than when it was before? Was it because it came down to negative?
No, it never gets to negative, right? This is somewhere very high. So basically, so the point, okay, so if we do this, so this is the direct, here we are, right? And this is the direction on which we are doing line search, right? So this looks like something like, you could even plot it exactly, right? This will look like something like this, okay? So here, the minimum will be somewhere here, right? But the minimum is on this plot, that's here. Because this completely ignores the rest of the space, right? It's looking only in this direction.
Is that because this is a step size of 1 now? It's picking that particular point?
No, it's not 1. It's the optimal step size. we really go to the minimum. The step size is 1, that would be a different story. That would probably converge even worse.
Right.
But this is already doing. This is really always finding the optimum. I guess this would be really made clear with like some 3D visualization, right? I admit I also don't have the picture in my mind, right? But if you really displaced like this ellipsoidal ball and sliced it with this, you would see that the optimum is really here. So what happens? It essentially overshoots in a sense, right? I mean, I think at this point I'm only confusing it, I suppose, because this is not so complicated. But it's essentially overshoot. Like if it got here, if it got to the 0. Then the gradient would be pointing in the good direction, right? Then the gradient would be pointing here, and you would get there immediately. But that just won't happen because we started here. Yes, for some starting points, you could be very lucky, you could get there quickly. But that's only a matter of luck. Okay, so the way we get around this problem is by employing Newton's method, which essentially provides us with a better descent direction. So we call it the Newton step. And let's call it x Newton. Maybe we could do like GD, like gradient descent. And the Newton step is by definition the minus Hessian of G, evaluated at x, of course, inverse the gradient of G. So it's almost the same thing as gradient descent, the only difference being that we multiply by the inverse Hessian at that point. Okay, we are somewhere, we started the initial guess, we evaluate the Hessian at the initial guess, we invert the Hessian, we multiply the gradient with it, and with the minus sign, that's the Newton direction. Why, or where did this come from, you might be thinking? Well, the idea is to find the direction x Newton so that we minimize this function. So if we take a function g, so if x is where we are, that's our current position, we can write a function that looks like this, gx plus gradient g transpose z plus z transpose the Hessian of g z. The gradient and the Hessian means evaluated at x, okay? So what this is the best fit quadratic approximation of the function g at point x, okay? So in 1D, it's sort of easy. If I have some arbitrary 1D function, right? And if I say this is my point x, then the best fit quadratic approximation would look something like this, right? And then maybe here we'll start deviating from it because this function is not, this is my g. This is not quadratic, some arbitrary function, say it's convex. And at this point, I find the best quadratic approximation to that function locally. And that's what this is. That's what the Hessian does, right? That's what we talked about when we talked about differentiation. The gradient is the best first order approximation. The Hessian is the best second order approximation. And the Newton step essentially means that if you take the full Newton step, if you do the t equals 1 step, if you do x plus delta x and t, what happens is you get to the minimum of this optimal quadratic approximation. So you will take the step right here. Okay, so you are here. You establish the optimal quadratic approximation. This is just an illustration. We are in multiple dimensions, but the idea carries over to many dimensions. You do the best fit optimal approximation. That's what the Hessian is needed for. You solve for the x and t. That would be the vector that gets you here, x and t, or delta x and t. And here the x plus delta x and t is where do you want to go to minimize this quadratic approximation. That's the idea of Newton's step, or the Newton descent direction.
Why the inverse?
Hmm?
Why the inverse?
Why the inverse? That's well. Think about this, right? What you would need to do. So if you want to minimize this, then you take the gradient of this and set it to 0, right? So what I guess I could do it, right? So if I take the gradient of this and set it to with respect to z, right? Because this is x is fixed here, z is the function. So if I take the gradient with respect to z of my g, then I will get the gradient of the original g without the hat. So don't let that confuse you. Plus the Hessian times z, right? Now I want to set it to 0, and now you can see where the inverse is coming from, right? This Hessian needs to get inverted. Yep. Okay. There's different ways to understand the Newton step. You can read that in Boyd if you're interested. The point is, guess how this works on this example. If you run the Newton's method on this case, from the same initial guess, the same problem, do you know what Newton will do? You do? How many iterations will Newton take? So here we took, I don't know, a lot of iterations, depending on how big accuracy we want, right? Usually you iterate this until you run out of like floating or double point accuracy, so you have it like accurate up to, that's what at least the optimization people like to do. So depending what accuracy you're looking for, right? But if you want a reasonable accuracy, you need to do a lot of iterations here. How many iterations you will need with Newton's method? 1 iteration. Because that's sort of like a catch. This is already a quadratic function, right? So in that case, this approximation is not an approximation, it's exact. So the line search will say, what are you asking me? Like t equals 1 is already the optimal step, right? So that will already solve it. And in the general case, then of course, generally you are not optimizing a quadratic function. You are optimizing a more complicated function. But the quadratic approximation is just a much better fit. And most importantly, it's affine invariant. It sort of doesn't care how much is it squished, right? That's what matters. That's what happens even in mass spring systems a lot, where the springs are usually very stiff because you don't want it to deform too much, which corresponds to highly squished ellipses. But Newton can deal with that no problem. Okay. Well, I have a lot of other stuff to cover, but I guess I should let you go to your next class. So I guess I will stop it here, and we can resume on Wednesday if that's okay. All right.